Okay, good morning and welcome everyone to the concurrent session 1. I am Assistant Professor Pirapat Thongnuk. I am a chairperson for this session today. So the first talk that we are going to have is going to be presented by Associate Professor Dr. Suparak Prasatham from the Faculty of Engineering, Department of Chemical Engineering. Please give a warm welcome to Associate Professor Dr. Suparak Prasatham.
Okay, thank you very much. So I will start my talk. So for the first 10 seconds, I will let you scan this QR code to get the whole slide if you wish. So as you can see, the topic is quite long. So for the next slide, I will break it down into keywords. So these are the keywords that explain the whole project. So first one, what we did is that we developed the public catalytic materials database. So we use the techniques in the quantum chemistry, AI, and also the high throughput experimentation. And the last two keywords is that the application of this one. So by using this catalytic materials database, we can discover or optimize a higher performance catalyst for the treatment of the harmful gases for the coal-fired and gas-fired stationary power plants in Thailand, which is the main type of power plants in Thailand. Okay. And so, as I told you, we use quantum chemistry, AI, and also high throughput experimentation to construct the database, as you can see here. So when we have the database, then we can learn and provide the insights when we scan for new materials. Yes. So and as you can see here, if you have the stationary power plants, it produce not only electricity but also the toxic gas like the NOx and carbon monoxide and also unburned hydrocarbons and also CO2, of course. So we divide it into two parts. The first one that we must tackle is to use the three-way catalyst plus with the SCR, which is the old technology. But still, since we still use the stationary power plants, we must get rid of the NOx, CO, and unburned hydrocarbons. So from this first part, it will transform this into a less harmful one, like water in the form of steam and nitrogen gas, and also more CO2. So as we get more CO2 plus the CO2 that was generated before, we have to input it into the second treatment, which is the CO2 reduction reactor. So we have two parts to screen for the catalyst, which is for the TWC and the CO2RR, using both the machine learning and the quantum chemistry. Okay, so these are four objectives. So the most important one that I would like to emphasize is the second one, to promote the research equality. So it means that we provide the free materials database so that anyone can use to start the research in the materials. Okay, so the talk will be divided into three parts. So first one, I will talk a little bit about the center in which I'm in. And next, I would explain how we use the data-driven versus the last part, the quantum chemical catalyst screening. Okay, so the center has long been established as the catalyst laboratory in 1979 with these only two machines, just a two furnace and a GC. And now we have 11 faculty members and around 120 plus of postdoc plus master and doctoral students. And so this part of the work came from the high performance computing unit, so which is the performance is around 20 teraflops. So this is the two layers of funding of the center. The top one is the funding with the large company, in which we use the money to generate these two center. The computational one and the industrial project that deals with the small and medium-sized company. So I'm in charge of this computational one. And what we did is that the whole group do the heterogeneous catalyst screening and design using the multi-scale computational techniques. So in terms of the multi-scale, you can see that we have the nanoscale, in which all of them do the quantum chemical calculations, so that we have the data to be input to the second team, is it micro, meso, and macro scale, that use machine learning together with the microkinetic modeling and the CFD, also the process simulations, to upscale the simulations and provide insight at the higher level. And we have a small wet lab team to validate the computational results. Second one, let's see the data-driven, which will be based on these two works that has been featured on the cover photos. And for the catalyst design, you can do two things. You use the pure experimentation, or you can use the computational techniques. So for the pure experimentation, it has long been used, like 40, 50 years. So if you have a lot of time and if you are rich, you just use the top one. But if you want to save cost, you can apply the computational techniques to lower the cost of the chemicals and the time used. Okay, so machine learning for the people outside the field. So for example, you open the YouTube and you listen to one song. So how can they know and suggest the related songs on the right side of the screen? So it learns from not only your data, but also other people's data that has access to this song, and also the data of the song itself, like the genre of this song, the artist, or the tempo of the song, for example. So likewise, we construct the materials database. As I told you, together with JICE in Japan, in Kanazawa, to predict the alloy catalyst, so that this can be used to screen for a higher performance catalyst for the TWC that I told you earlier. So I will not go into this in detail. You can, as you can scan on the first slide, you can see all the work later. So I will skip to the second part. So this we use the techniques other than the artificial neural network. We use the Gaussian process regression to explain the active site on the catalyst and predict the possible active site for the water activation, which is one of the steps in the reaction that will mitigate the harmful gas that I told you earlier. Okay. For the second part, since I have 2.5 minutes left, I will go to our signature work. So this one is our own screening tools. It's pure computational. It was developed since 2017, and it has been published in these 5 articles. The latest one is on the bottom right corner in ChemCat-Chem. So as I told you, this is the second part of the treatment of this CO2. So one way to reduce CO2 is by the utilization of CO2. So one, like O reaction is the dry forming reaction. So it reacts to greenhouse gases, which is the methane and the CO2, to form the syn gas. So now if you can focus more on the to produce more of the hydrogen at these days. Okay. So the main problem is that the deactivation of the catalyst. So what we must do is that we must get rid of this problem, because this one caused the regeneration and replacement cost of the catalyst. So by designing a more active and stable catalyst, we propose this ratings concept, which is based on the ability of your materials to activate the CO2 and methane, and the ability to remove and to form the coke. So by evaluating based on these 3 abilities, we can compare different catalysts. So I will skip to the construction part. So what we must do is that we must have a standard plot to see if, for example, you have a new material. So where will this material be in this map to screen for the active and stable catalyst. So then we construct all of this based on the, for example, the reactivity. We consider the rate of the total reactions, and for the stability, we must see both sides, the formation of the coke and the removal of the coke. So by intercepting these three, we can see that the desired region is that the intersection between the coke-resistant region and the active regions. And then we ended up having the catalyst, the desired catalyst, to just be in this yellow zone. Oh, sorry, this yellow zone. So this is the active and stable region. So if you have a new materials, you now can screen for the new catalyst. And if it's out of this zone, it may be less active or less stable. Okay. And thanks to the funding from the Asahi Glass Foundation, we can publish 4 articles in Tier 1 journal based on this project. And also we publish this database in which is free to access. Okay. So lastly, this database will provide at least a fundamental data for the research, and also for higher applications, it can also be a good starting point. And lastly, I would like to thank the center and also our team in computational groups, in which this is the computational resource from our in-house. Okay. Thank you very much.
Thank you again, Dr. Suparek. So, is there any question from the floor, from the audience?
Yes. Oh, it's very interesting, nice presentation. Thank you very much. Maybe in the as for the bimetal or trimetal catalyst for to recover the carbon dioxide to carbon monoxide and hydrogen. Maybe reaction rate is very important, and to reduce the formation of coke is also important.
Yes.
And maybe if the bimetal or metal particle might be allocated or something,
So,
maybe it is very difficult to regenerate the catalyst. So could you have some reduce allocation or regeneration to regenerate the catalyst, catalytic activity or catalysts?
So for the, as you say, that one is called sintering, right?
Right.
The agglomeration of the active site.
Yeah.
Okay. So in that part, like typically what they did is that they need to redistribute the active site again. It's already aggregate and you cannot like separate it.
Okay.
So yeah, so you can do many things like make it as the, how to say, oxide form again to let the oxygen separate the active site, and then you reduce it later. So you have the separated small active site again instead of the big one. And also this one can also predict, because when you have a larger particles, the ratio between the facet, for example, the configuration, it changed. So the ratio between each facet in the small particles compared to the large one, for example, 1 nanometer diameter of the particle versus the 10 nanometer diameter. So that one has different ratio between these phases, and this each facet had its own activity. So when you even out and get the average rate for each particle is different. So this one can predict if it's we have lower stability also. And as I told you, the sintering can be managed in the industrial scale with the same method.
So then maybe it's very difficult to compare just the bimetal means just alloy or two compositions,
two connected
group,
particles. So for example, if you have a nickel iron, if it's nickel combining with iron, or it's just a completely mixed nickel iron, right? It's your question. So that one we need to model each of them we need to model the pure iron and the pure nickel, and then the combined phase of nickel and iron. So each of that surface is now different, and you measure the rate of reaction, and you see if the rate of from your experiment is the same as the mixed one or the separated one that has been averaged. Yes.
Okay.
Yes.
Thank you both for sharing thought. So I think we are run out of time, and we have to go to the next speaker, Dr. Thirayut Saad. And because the title is quite short, so I'm going to read it out. Plastic separation using hybrid jig for resources recycling. Effects of geometrical properties of particles on the apparent density and separation. Dr. Thirayut Saad is from the Department of Mining and Petroleum Engineering, Faculty of Engineering. So please.
Okay, thank you. Good morning, everyone. So I am Thirayut Saad from Mining and Petroleum Engineering. So the title as the share already presents. So let's go to the next slide. So first, I would like to little bit explain about why I'm doing the research related to recycling. My laboratory named Mineral Processing and Resources Recycling, and our department named Mining and Petroleum Engineering. Usually, we can divide the source of resource into two, that is the primary resource and secondary resource. So the first one, the primary resource, we can extract from the earth as the natural resource like petroleum or ore. After that, since the resource that we extract is not pure, so we have to purify or separate to concentrate the thing that we want, like valuable things. So we need the separation process like mineral processing to separate the valuable material from the other. After that, we can recover and utilize it as energy and also resources. So after we utilize, this resource can turn to be the waste. So actually, the resource contained in this waste are the same as product. It contains the many valuable things. So we can use the separation method that used in mineral processing to apply for resources recycling to recover this valuable material to utilize it again. So this research, I focus on the plastic. So there are many management for plastic waste. So in ideal, in the highest sustainability level, we should do it as the material recycling. However, we need to make sure that it's clean and it's separate well from the other. So plastic separation is needed. So however, it's quite difficult. So sometimes only the easy separation is used, like we do the zinc force separation to recover the float plastic like the polyolefin, PP, polypropylene, or PE, polyethylene from other, and then we can make the material with lower grade. So, but other mostly go through the insulator for thermal treatment or energy recovery. However, some plastic have the effect to this process as well. For example, PVC, that after we burn the chloride or as well as the dioxin is generated, that affect to the process itself and also environment. That's why the dirty plastic mostly go to landfill. So as I just explained in the previous slide, so plastic separation is very important for waste management. So in this study, I apply the Takuya that commercially called Bartek jig that usually used in coal cleaning for separate coal and rock to apply with plastic separation. This jig is quite easy operate, and also we can make it high capacity as well as it's good for environment since the chemical reagent is not needed. So we use the density separation to separate the heavy one have the higher setting velocity. So due to the pulsation of jig, we can separate it. So we to separate the particle based on specific gravity, we need to know the specific gravity of particle as well. If the specific gravity is different, so it's quite easy to separate. However, some plastic have a really similar specific gravity, so it's difficult to separate. So for the research that I got the funding from Asahi Glass Foundation, so I focused on the PET and PVC. So this is example of the flow chart for plastic separation. So it can be shown that it can be separate. However, some plastic is difficult, like PET and PVC. So our research related to the plastic separation, we developed 4 kinds of advanced jig for plastic separation. Since plastic have many properties, like some plastic is sinks, some plastic float, some plastic have a quite different specific gravity. However, some is similar. So we develop various jig to suitable for each material. In this topic today, I focus on the hybrid jig. That is the combination of gravity separation like jig and the surface wettability separation like flotation. So this is example of the utilization of advanced jig for each type of plastic. So however, in the case of recycling, it's quite different from ore. So since the plastic or another kind of waste, once we crush it, it remain many material and also the size and shape. We can find the copper wire and thick plastic as well as thin plastic that affect the separation. So in this study, I used PET and PVC to crush and check the shape property of the plastic. So after that, I check the shape distribution. The results show that for the thick plastics, the crushing behavior is quite random. However, in the case of thin plastic, the size reduction only occur for some direction. Like in this case, it's quite difficult to crush in the short dimension that is thickness. So that make the size and shape change with the crushing, as well as not only sphericity of fatness ratio and elongation ratio. Roughness also change. Once we reduce the particle size, the new surface is generated, and compare between new surface and the old surface. The new surface have more roughness compared with the old surface. That also caused the separation effect to the bubble attachment as well. So since jig is gravity separation, so I also check the setting velocity measurement. It's both for that not only specific gravity and size, but also particle shape affect the setting velocity. Not only that, since we do hybrid jig is combination of gravity separation and flotation, that is surface availability. So we check about the bubble attachment evaluation volume to understand how many bubbles attach on the particle and how the apparent density change with the shape as well as other conditions. Results show that the similar value of specific gravity apparent is shown. Since, as explained in previous slide, the shape is changed and also the roughness is changed. Sorry here. So the thin surface, the thin shape that have the more surface, it have a low roughness. However, the sphere-like shape that have a low surface, it have a high roughness. So it seems like these two property is effect of these two property is negated. So it shows the similar apparent density. After that, we check the jig separation. The result of jig separation and hybrid jig separation show in this slide. So in this case, to make it easy to understand, I use the one that thickest and the one that thinnest one. The results show that for the jig separation, the separation is quite different. Sorry, its location is mistake. So the jig separation is here and here. So the purity of plastic is 90, 69, and 61. So, however, in the case of hybrid jig, since the bubble attachment and fatness ratio as well as purity is go in the opposite way, so effect is negative. So we can achieve the similar value. So this is conclusion. So for this light particle is changed with the crushing. However, for sphere-like particle, the size reduction is random in each direction. Setting velocity, we also can see the difference, the attached bubble volume, since the effect is negative, so we cannot see the difference. So finally, jig separation and hybrid jig separation results what in line with the setting velocity measurement as well as the attached bubble volume evaluation. So for the future plan, so right now we are trying to, how can I say, like estimate the separation efficiency using the setting velocity measurement results as well as the estimation of the hybrid jig separation using attachment bubble volume. Finally, since this plastic is quite close to each other by the specific gravity, so we can adjust. We can try to adjust to the separation by water pulsation as well as using the wetting agent to change the surface wettability. Okay, that's all for presentation. Thank you.
Thank you, Dr. Thirayut. Is there any question from the audience for Dr. Thirayut? Yes, please.
Okay, yeah. Thank you very much for your nice presentation. And so you you want to separate the PET and PVC.
Yes.
And the goal to achieve the separation ratio, maybe 99% PET and 1% PVC can be used for blah, blah, blah.
Yes, yes.
Yeah, maybe is it a target composition ratio for the PET PVC polymer blend?
Okay. Let's back to the results we achieved right now.
Yeah.
Since, as I explained, the property of specificity in PET and PVC is quite similar. Like now we have 1.31 and 1.38. So it's actually in theory it's impossible to separate it in gravity separation. But in this case, we apply the flotation to help. So today, as I show here, I divide it into only two. So as you know, the separation will quite not good, but we can separate. However, in the real case, actually I divide it into 6 layers from top. So the 6th layer we can achieve around 90 and 100% as well. What to show is 6 layer and show many conditions. It's quite really similar value to see. So I didn't show it today. The one more things to achieve that things is by using the surface wettability control by a kind like surfactants. So, but the goals now we also consider about the environmental issue as well. So we try to not to use the wetting agent at first. However, by using this jig separation and hybrid jig separation before, without the effect of particle shape, we can achieve the 99% as well as sometimes 100%.
Thank you. Thank you, Dr. Thirayut Pheng Saat. Please give a round of applause to Ajahn. So next speaker. So our next speaker is Dr. Pichaya Inna from the Department of Chemical Technology, Faculty of Science. Unfortunately, she is not here with us, so she gave us a video presentation that we are going to give it to you now. Please.
Hi everybody, my name is Dr. Pichaya Inna from the Department of Chemical Technology here at Faculty of Science. First of all, I would like to apologize for not being able to make it here at the Asahi Glass Foundation event. However, I hope that my video presentation will compensate for it one way or another. Here in this presentation, I would like to present my research work entitled Bioelectricity Production from Algal Biosolar Cells with a Nature-Inspired Honeycomb Structure System. My co-researchers are Professor Dr. Chavalit Ngamsarasivichai and Assistant Professors Dr. Kamon Thinsura. The outline of these presentations are divided into 5 main parts. The first one is introductions, the second is methodologies, results, conclusions, and future work. Let's start with the introductions. Due to the continuous growth of the world populations, there is an increasing demand for the clean energy sources. One of the attractive and recent innovation is biophotovoltaics, also called in short BPVs, which can potentially produce sustainable electricity because it can produce 24 hours electrical supplies both in day and night time. It is also able to capture carbon dioxide, which is one of the troublesome of the greenhouse gases emissions. And another perks of this technology is that it is a self-recover technology where it's used the living microorganisms that if we feed them the right amount of nutrient supplies, it can recover itself if there is any photo bleaching or any photo damage. Despite all the promising benefits, one of the major disadvantages of the BPV is that it still produces a very low current output. By drawing an inspiration from nature, like designing the system with a honeycomb structures that actually has been recently implemented with solar cell technologies. However, it has not been implemented with the BPVs yet. So with this nature-inspired structures, it can potentially reduce the reflection loss as well as improve the absorption rate of the infrared light into the system so that it can enhance the power output. So the research work hopefully will contribute to the Sustainable Development Goals number 7, which is affordable and clean energy, as well as goal number 13, climate action. Next, let's move on to the methodology. For the methodologies, we divide it into 4 main stages. The first one is the cultivation of microalgae strains. The first microalgae strain is Corella species, and the second is Corella vulgaris TISTR 8580. Then we designed the BPVs with 3 different structures. The first one is honeycomb structures, the second is diamond, and last but not least is the planar structures, which we treated as a control. Then we performed the toxicity and adhesion test to find the most suitable amount of acrylic polymer that we used to mix microalgae and attached onto electrode. This will create the immobilization system, which is more stable than the suspension system. And last but not least is to test the algal biosolar cells for the bioelectricity productions. And here we compare between two systems, the immobilization and the suspension. The purpose of adhesion and toxicity test were to find the level of non-toxic acrylic polymer amount and also enough affinity for the cells to bind onto the copper electrode. So for the toxicity, we expose the cells with different formulated ratios between cells and acrylic for 7 days period and check whether the cell grow or not. For the adhesion test, we dry the cells and acrylic formulations onto the copper electrode and put the samples onto the checker at 80 rpm to investigate how many cells released from the electrode into the water after 72 hours. For the bioelectricity test, we investigate two parameters. The first one is of course the structures that we vary 3 levels: honeycomb, planar, and diamond. We also try to compare between the immobilization and the suspension systems to see what kind of enhancement we could potentially do if we decide to do the immobilization rather than the suspension arrangement. For the immobilizations, here is the pictures of the algae coated on the electrode, which is going to be on the anode side. The way we test the bioelectricities, we connect the algal biosolar cells that we developed to the multimeters so that the anode and cathode connect together, and the electrons that produce from the algae can flow through the multimeters to the cathode side, and that is where we measured the current output, the voltage, and we calculate the power output after that. Here are the prototype of our algal biosolar cells with 3 different structures: honeycomb, diamond, and planar. We also have a little small video clip for you to see in 3D. Let's carry on with the result. From the toxicity test, it shows that both microalgae strains did not cope well when we increased the amount of polymer into the mixture. And as you can see, beyond 5% of the acrylic polymers, the survival rate is very low and it went very negative. For the adhesion test, as we increased the amount of polymers, it actually decreased the percentage of cell released from the electrodes. This means that by implementing the acrylic polymer with the microalgae, it actually makes the microalgae attach better. The same effect also applied to the Corella vulgaris species, where when we increase the acrylic polymer just a tiny amount, it's actually attached onto the electrode better than the Corella species. This may due to the fact that Corella vulgaris like to agglomerate anyway in nature. So once we evaluate the data that we obtained from the toxicity and adhesions, we found that the suitable amount of polymer for Corella species was 5%, while the Corella vulgaris only need 2.5% polymer. For the result of the bioelectrical current output, as you can see that in most cases, the immobilizations enhance the current output compared to the suspension ones, and the highest current output that we achieved was the BPVs with diamond-shaped structures with Corolla vulgaris, and the current output was 0.523 milliamp per meter squared. For the voltage output, we achieved the highest voltage output from immobilization system of Corolla vulgaris with the honeycomb structures. The highest voltage output was 0.104 volt. The last result of the bioelectricity test was the power output, and as you can see that is very similar to the current output, was that the immobilization system was enhancing the power output compared to the suspension ones in some cases, and the highest output that we achieved was from the diamond-shaped BPVs with the Corolla vulgaris cells, and the highest power output was 0.0229 millivolt per square meter. Let's conclude our finding. We conclude that we found the right amount of acrylic polymer that's supposed to be used for these two microalgae species, that if we want to use in BPVs to attach onto the copper electrodes, and we can conclude that the diamond shape actually generate the highest power density for Corolla vulgaris, followed by the honeycomb structures and then the planar. From our studies, we found that the diamond-shaped structures, BPVs, with Corolla vulgaris species enhance the electricity production to the maximum compared to the conditions that we tested. So to conclude and emphasize again that if we use the nature-inspired structures, we can enhance the power generations for algal biosolar cells. And this research work, we also put this research work into competitions for the Hitachi Trophy competitions, and we won the second prize for this research work. We also presented this research work in PPC and Britomat symposiums and won the bronze prize for the best poster presentations. Last but not least, future work. So for the future work of this research work, we want to explore three main things. The first one is the efficiency enhancement. Hopefully, we will be doing the optimization of the light absorptions in this algal biosolar cell systems so that we can improve the efficiency and enhance the electrical output further. The next is the integrations with the energy storage. So there's a new trend going on that we need to be able to store energy, not just only the generation of energy. So by integrating the algal biosolar cells with energy storage, we could potentially have the self-sustaining system to generate, store, and utilize electricity whenever we need it. And last but not least is the scalability and manufacturing. We want to try and connect the algal biosolar cells together in series pattern to generate higher electrical output. The one that we are trying to do in the progress in the meantime is to register a patent of our prototype, and At the moment, we're trying to write one of a paper on the Q1 or Q2 level. So I would like to acknowledge some of the people, especially my bachelor student, Mr. Narongsak and Miss Wanida. They both work really hard on this project, and Professor Dr. Chawalit and Assistant Professor Dr. Kamon, who's looking over all this research work since from day one. And last but not least, I would like to thank the Asahi Glass Foundation for giving me an opportunity and supported me financially to do this research work. Thank you for your attention. I hope you like these video presentations. And if you would like to check out my research group, which is called NIAP Lab, please feel free to scan the QR code to check out our website. Or if you have any questions, please feel free to email me pichaya.i@jula.ac.th. Thank you.
Right. I strongly believe that Dr. Pichaya will significantly contribute to the sustainable development on electricity production. And if you have any feedback for Dr. Pichaya, you can leave it to me, and I will make sure that the message is passed on to Dr. Pichaya after this. So we have a very tight schedule, so I'm going to move on to the next video presentation again by Dr. Sorapat Niyom Sin. He is not here with us. He is from the Petroleum and Petrochemical College,ฬาลงกรณ University, and he's going to give a video presentation on biodegradable hydrogel covered with thermoresponsive polymer for prolonging water holding ability at elevated temperature. Video. We have a technical problem. Please hold on a bit. So, because of the technical problem, we are going to skip to Dr. Chitti Kasem Chainan, and we'll move back to Dr. Sarapat clip again. So, Dr. Chitti is from the Department of Chemical Technology, Faculty of Science, and his talk is going to be on primary battery recycling towards circular economy and environmental sustainability.
Okay, yeah. Good morning, everyone. Okay, yeah. First of all, I'd like to thank Asahi Glass Foundation for funding this research, and also all the person here as the list in this slide for all the help and contribute to this research. Yep. Okay, so my talk today would be about I try to revive the material inside the spent primary batteries. This spent primary battery, I think you know, and you experience the usage of this kind of batteries. I think in every household, you would find that in the remote control, electronic door lock, or alarm clock, and etc., etc. And then try to reuse the material inside these batteries for another kind of batteries that I would talk later. So the outline of my talk today would start from the objectives of this research, and then would be the introduction, methodology, results, and discussion, and then the conclusion. So the objectives is first to try to optimize the preparation conditions for the manganese compound, like manganese oxide, manganese sulfate, from the spent alkali batteries, and then try to prepare the manganese dioxide from the spent alkali batteries and test as an active material in zinc-ion batteries. Then I think it would be nice to just know a little bit on the alkali batteries. And the alkali battery shown in this schematic would contain the main components. Let's see from the first one about the positive electrode. The positive electrode contains manganese dioxide and carbon. And then the negative electrode contain the zinc powder. And then these batteries cannot work without the electrolyte. And then we would have the electrolyte of the potassium hydroxide. And this potassium hydroxide would be soaked up on the polypropylene separator. And then as you can see from the outer appearance of this battery, they would have the kind of metallic jacket or metallic case cover or these kind of materials. Okay. And if we look at some figures, these kind of battery are being produced around the world with the approximate value around 3 billion units per year. So that make the huge amount of this kind of batteries being used around the world. And then according to the EU statistics, just 50% of these kind of batteries are recycled. So that means the rest of this kind of battery are just gone simply to waste. And waste disposal for this kind of battery is just for the landfills. So you could imagine that if we just put this battery waste into the landfill, it would create adverse effects to the environment. And also we would lose the potential of recycling the hidden potential of the manganese or zinc or other compounds in this kind of batteries. So if we would like to recycle the compound in this kind of battery, we should be able to understand what actually inside this kind of battery. So if we just take a look at this chemistry of this battery, as mentioned already that from the negative electrode, we have the zinc or zinc powder. This zinc powder would undergo the reaction and convert itself to zinc oxide. And then at the positive electrode, the manganese dioxide or manganese 4 oxide. This manganese has the 4 plus in the oxidation state. And then after the conversion, it would be the manganese 3 oxide or the oxidation state of the manganese reduced to the 3 plus. And this manganese 3 oxide is the main focus of my work or the scope of my work for the recycling. And if we dismantle the battery, we would see that the part on the circular mark here is the manganese 3 oxide that to be used for the recycling process. So from the methodology point of view, if we start from the manganese 3 oxide, we'll try to convert this manganese 3 oxide by using the heat treatment under nitrogen gas atmosphere to convert manganese 3 oxide to manganese 2 oxide. And then with this manganese 2 oxide, later it would be converted by acid leaching or just simply dissolve this manganese 2 oxide to form the manganese sulfate. And then from the manganese sulfate, it would be taken to react with the potassium permanganate by the chemical precipitation to form the solid manganese dioxide again. And this procedure actually is the subset of the main classification of the pyrometallurgical methods or hydrometallurgical method. And if you have a look in the literature, you can find that in some research, they can just use the pyrometallurgical method alone or hydrometallurgical method alone. But why we choose this combination? Because if we try to imagine that when we use the pyrometallurgical method alone, that means we can just simply put a battery into a furnace and then let it burn and let it transform, all the metal would be fused together and then would form a kind of not very applicable compound. But if we use the hydrometallurgical method alone, we would involve a lot of kind of expensive chemicals that is difficult for the scale up or industrial scale. So then if we take a look at the application, we could see that a range of application could be drawn from this compound, from the animal feed, fertilizer, pigment in ceramics, or paint, and then Zinc-Ion battery is the main focus here. So for the result and discussion, first, if we try to heat treat the manganese 3 oxide from the spent battery, we would form the manganese 2 oxide. And this XRD pattern confirm that from the 950 degrees Celsius, we would have almost purely manganese 2 oxide in our compound. And then from the XRF or elemental analysis, we could see that the percentage of the manganese can go up to around 64%. Yeah, and the chemical reaction can be seen in this slide. And then when we try to leach or we try to dissolve the manganese 2 oxide to manganese sulfate, when we try to vary the amount of acid, we could see that with 20% excess of the acid, this sulfuric acid, we would achieve up to 98% of the leaching efficiency. So that means we almost dissolve completely of the heat-treated compound. And then lastly, we would try to convert the manganese sulfate into the manganese dioxide by the chemical precipitation. And with the specific temperature of 60 degrees onwards, we could achieve more than 99% of the manganese dioxide compound. And then from the electrochemical test that we do for the Zinc-Ion battery, we try to compare the performance of the our synthesized manganese dioxide with the commercial manganese dioxide. It could be seen that from the cycling test, it showed the comparable performance between the synthesized manganese dioxide and the commercial manganese dioxide here, as you can see from the capacity curve here. Of course, the capacity of the synthesized manganese dioxide is a little bit lower compared to the manganese dioxide, but the range of the value is still comparable. And then for the conclusion, we demonstrate that we try to combine the pyrometallurgical and hydrometallurgical techniques to synthesize the compound of manganese in a sequence way of manganese 2 oxide, manganese sulfate, and manganese dioxide. And then we demonstrate that this manganese dioxide that we synthesize can be used as Zinc-Ion battery, which is rechargeable battery better than the original state of the primary battery that is non-rechargeable. Yep. Okay. Thank you for your attention. Yep.
Thank you, Dr. Chitti. Is there any question from the audience?
Okay.
Yes, please.
So you mentioned applying a manganese dioxide can be used for the rechargeable battery.
Yeah.
Have you examined the systems using manganese dioxide for the rechargeable batteries? I mean,
you mean not the Zinc-Ion one, or
so can you make sure the activity of manganese oxide for the rechargeable Zinc-Ion batteries?
I think from this electrochemical data, I think it can prove the concept like this synthesized manganese dioxide from the spent alkali battery can be used. Yeah, if we compare with the commercial manganese dioxide, this one, and I'm sorry, I forgot to mention that this commercial manganese dioxide is the same grade that the same battery grade that present in the alkali batteries. Yeah.
Or is there any other small amount of metals contaminations from the used batteries?
Yeah, there are. Yeah. For example, when we do the XIF analysis, we would observe this kind of zinc, for example, yeah, with around 1% approximately by weight. Yeah. In this.
These metals can you remove from the manganese compounds? Compounds. Which kind of metals are contaminated in the mangan oxide?
The metal is the zinc, like in this slide here, the zinc compound. But the compound actually, because from the XRD data, it does not show the crystalline phase of this zinc compound. So that's why it would be difficult to say like what kind of compound it is. But we suppose it should be zinc oxide, but maybe the crystalline is too small or is in the amorphous phase.
Okay.
Yeah. But if we use in the Zinc-Ion batteries, then it should be okay because anyway we would have zinc. Yes.
Thank you very much for your presentation. I think your proposal of recycling is very excellent. My question is, what stage actually are you currently in toward achieving it, assuming commercial application?
Oh, yeah, actually, because this work we done in collaboration with other kind of researchers. So yeah, we try to aim for the commercialization as well, but still, I think the first limitation, and I think would be a kind of big limitation for us, is that have to say how we're going to gather all the spent alkali batteries, because we have to admit that our recycling system in Thailand is not exactly a kind of in the perfect level, right? For example, this sample, what we use right now, the spent alkali battery, we receive from the university waste collection points. Yeah, yeah. And
now, in my understanding, you already prepare the concept of the recycling from the viewpoint of academic point, and but the issue remains how the other.
Yeah.
Blah blah.
yeah,
Understood. Thank you
yeah,
very much.
yeah. Okay.
Thank you, Dr. Chitti. And so we are going to move back on the schedule to the video presentation by Dr. Sorapat Niyomsin. He is from the Petroleum and Petrochemical College. Please bear with us a little bit. All right.
Everyone that I cannot be. Morning, everyone. I'm Dr. Sorapat Singh. First of all, I would like to apologize everyone that I cannot be in the event. by myself, okay, as I need to join the workshop outside July. Okay, so today I would like to present my research work under Asahi Glass Foundation scholar, okay, which is the hydrogel, bio-based hydrogel, which has also special behavior with the thermoresponsive function. Okay. In this product will be potential use in the water holding application. So let's talk about the bio-based polymer and bioplastic. Nowadays, the concern of the use of the material from the petroleum need to be reduced as the problem, as everyone know about the global warming resulting from the carbon dioxide emission. Okay, so scientists try to develop new material from bio-based material, okay, to substitute the material that come from the petroleum base, okay, and shift to the bio-based. Another thing is the hydrogel. Okay, hydrogel is one type of the polymer. Okay, one type of polymer that can be used for agriculture application. Okay, in agriculture application, if we carry out the agriculture in the drought area, okay, you need to put a lot of the irrigation or artificial rain to overcome the drought of the land. So if we have some kind of the hydrogel or the absorbent that can hold water during the drought, okay, so in that case it will help in restoring the water inside the soil, okay, and even it is at high temperature. Okay, so the basic requirement of the hydrogel that can be used in this application is it should be non-toxic to environment, and it should be biocompatible and should hold high water content inside the structure. Okay, and at high temperature, normally at high temperature, water tend to be evaporate out. Okay, and what if we have something that coated on the hydrogel and protect the water become like that, release the water out slowly, it would be better. Okay, so let's see how to prepare the hydrogel, okay, or the polymer gel. Normally, the polymer gel can be prepared in various types of reaction. Okay, maybe we can start from the monomer A, monomer B, and the cross-linker to prepare like the cross-link structure polymer. Okay, or we have the polymer which has many functional group and connected with the bifunctional group like monomer B. Okay, to be act as a cross-linker. In this case, we can also get the gel. And another type is supramolecular interaction. In this case, it is like the secondary interaction between the molecule. And the one of the polymer that is hydrophilic, which can be used to prepare hydrogel, is the starch. Okay, starch also the commercially available, and it can be derived from the natural. Okay, and many scientists already report about the starch hydrogel. They prepare the starch with the cerium ion to get the free radical and then polymerize with the acrylic acid, something like that, to get the starch gap polyacrylic acid. In this case, the gel can be formed. And also the starch can react with the citric acid. Okay, citric acid. Once the citric acid is under heat, it can form like the anhydride intermediate agent, and this chemical will react with the hydroxyl group of starch to perform as a cross-link structure, and in this case it is a cross-link starch. And this process is a clean process, as the citric acid is also come from nature. Okay, and it is biodegradable. Okay, and it also the environmentally friendly. Okay. How about another function? that we need to coat the hydrogel, which is the thermoresponsive polymer. What is thermoresponsive polymer? The thermoresponsive polymer is the polymer that can change its behavior at high temperature or low temperature. It will behave with different behavior. In this case, we call the temperature that change the behavior is the LCFT temperature. Okay. In this case, this polymer at low temperature it can form hydrogen bond with water, but at high temperature it will form the hydrogen bond with itself, and it behaves like a hydrophobic interaction to the water, so it will not dissolve in the water. The polymer that can act like this is the polyvinyl caprolactam and poly-N-isopropyl-acrylamide or polynapalm, which this different structure will have the different temperature that will change behavior. So in this case, I would like to choose the polynapalm, which has the temperature at change at 32 degrees Celsius. So how to combine the polymer, the hydrogel with the LCFT polymer? Okay. Normally, people try to prepare the whole polymer together. Okay. And in that case, once the LCFT polymer change the behavior to be hydrophobic, the swirling ratio will be decreased for the whole material. Okay. What if we coat the LCFT polymer, the responsive polymer, on the only outside of the hydrogel? Okay, it would be better because the inside hydrogel still contains some water, but the surface will protect the water to be evaporated out. So in this case, we can control switching on-off system. Okay. So in this case, we would like to design the material, the core material, which is the starch hydrogel, okay, and connected with the thermoresponsive function on the outside. Okay. So once we heat it up, the outside will be turned into hydrophobic interaction and protect the water to be evaporated out. Okay. So let's see. With the citric acid, okay, to get the starch CA, which is the cross-link structure of the starch. Okay. After we get the first product, okay, I continue to react with the acrylic acid. Okay. Once the hydroxyl group of starch react with the carboxylic group of the acrylic acid here, then the surface of the hydrogel will consist of the double bond. Okay. After that, after we get the double bond on the surface of the hydrogel, we will carry out the polymerization of the thermoresponsive polymer on the surface of the starch. Okay. Then we can get the thermoresponsive polymer on the surface of the starch hydrogel. Let's see the characterization. As this is the gel, okay, so we need to characterize the structure of the cross-link structure of starch, okay, by using FTIR. From the FTIR, you can see that the change of the signal at this position from starch and citric acid to be the structure like this. Okay, so it can confirm that the ester bond is formed. Okay, moreover, there is still hydroxyl group, okay, in this region, which means the hydroxyl group of starch is remain. So it would be work for the water holding application. For the second step, okay, that I incorporate the acrylic acid on the surface of the hydrogel. Okay. In this case, I also use the FTIR technique, okay, to characterize the formation of the ester bond and the existence of the vinyl group on the surface. In this case, you can see that after we analyze the deconvoluted FTIR spectrum, we can see the signal of the carbon-carbon double bond on the surface, okay, become more higher significant intensity of the carbon-carbon Q. Okay. After that, I carry out the polymerization reaction of the napalm on the surface here. And again, we use the FTIR spectrum. You can see that at the carbonyl region will become more complicated, resulting from a lot of the carboxylic acid. carbonyl group, okay, which consists of the ester bond and the amine bond and carbon double bond, something like that. Okay. So in this case, it will become more complicated. After we analyze by using a deconvoluted method on the FTIR spectrum, we can see that we successfully graph the napalm molecule, okay, on the surface of the starch hydrogel. And after we analyze the composition, okay, by using the thermograph TGA technique, okay, we can see that we get the degradation of the napalm, which can confirm that we successfully graph polynapalm on the surface of the hydrogel. Okay. So let's see the performance of the hydrogel. The hydrogel, first we put the hydrogel at the low temperature, okay, and once we heat it up to 40 degrees Celsius and measure the time, you can see that from the line with the circle, okay, at the very beginning for the first hour, for the first 2 hours, you can see that the hydrogel will is not swell, okay, which means the surface, okay, this might be the surface of the hydrogel turn from hydrophilic to be hydrophobic. Okay. Then the water will be hardly to penetrate inside the hydrogel, so that the hydrogel will remain the swelling ratio, okay? And then after that, after the time pass for like after 2 hours, okay, it start to be a little bit more water content absorbed. This might be because of the temperature itself, okay, that can cause the polymer will become more swollen. Okay. But at the low temperature, okay, at low temperature, the thermoresponsive function will not change the behavior. It will remain hydrophilic molecule. Okay. It will remain hydrophilic molecule. Once we put it in the low temperature, like 10 degrees Celsius, at the very beginning, it is it absorbs a little bit more water. This might be due to the hydrophilic behavior of the polynapalm itself. Okay, you tend to absorb more water. Okay, and after that, after we put it for a while at the low temperature, it causes the polymer as the swelling ratio become lower. Okay, so after that, the water content of the hydrogel is decreased. Okay. So we would like to confirm that this swelling behavior change between high temperature and low temperature is because of the thermoresponsive polymer. Okay, so we investigate further by using the water contact angle. Okay, we put the hydrogel at a high temperature and low temperature. You can see that at low temperature, the water will start to absorb into the hydrogel, whereas at the polymer with the high temperature, the water can be hold on the surface of the hydrogel, which refer that the hydrogel, the surface of the hydrogel here turn into the hydrophobic behavior that can hold the water outside the hydrogel. Okay, so let's see the conclusion. I successfully prepared the starch hydrogel, okay, which is bio-based derived material, okay, and the surface of hydrogel was decorated with the thermoresponsive function, thermoresponsive polymer, which can switch the behavior between hydrophilic and hydrophobic behavior. Okay, and the hydrogel can maintain the water at high temperature, and the hydrogel might be suitable for applying in the agriculture application. Okay, last but not least, I would like to thank Asahi Glass Foundation, okay, for the research fund and the grant from the for the development of the new faculty staff, รัชดาภิเษกสมพูด endowment fund from จุฬาลงกรณ์ University. Okay. If you have any question about my research, okay, please feel free to contact me to ask the question by using email here or contact me by line ID here. Okay. Thank you.
Right. I have to thank Dr. Sorapat for the video clip, interesting video clip. And so I think we are running out of time, so I'm going to move to Associate Professor Dr. Jen Yuk Lo Wacharin from the Department of Environmental Engineering, the Faculty of Engineering. He is going to give a talk on optimized operation of slow and rapid sand filler based on relationships between microbial community structure and DOM, geometry, and biodegradability for small to medium scale waterworks. Please, Ajahn Jenjuk.
Okay, thank you, Mr. Chairman, and good morning, everyone. So, we just listened to the manganese in battery that presented by Professor Chitti, and according to very long topics, what I grabbed up here will be about the biological process that involved in the manganese removal in the sand filtration. Okay, what makes complicated in the water treatment is that not only the manganese and other metals that present in the water, but they also have several organic matter that present together in the water. The point is that due to the climate change and the seasonal variation, different type of DOM, it stands for dissolved organic matter, can bring into the water, and most of them are biological degradation, and some of them are non-biodegradables. So what the idea is that, what if these two pollutants coexist together in the water, and our typical water treatment process employ sand filtration? I think it's the same in Japan. If we have the very big full-scale water treatment in Thailand, we will employ the rapid sand filtration. But in the small scale, in the local province, normally we use the slow sand filtration. So we collect the raw water, and after treatment in several steps in the very big water treatment in Thailand, and this use the water from the river as the water for producing potable water. The collection of the sample is in 2 seasons, in dry and wet season. What I would like to have your attention is about the manganese level in the raw water. Of course, even it past the maximum allowable level that's set by the Thailand government, but the concentration is still high, and we need to get rid of this kind of pollutants more than 80%. The point is that most of the small scale and the new plant, they cannot achieve that level. So we try to do our best. What is the way that we can optimize the treatment process, including the sand filtration? And what could have attention is in wet season, we observe the contribution of the small tribbles that bring about the pollutants, especially you can see from the ammonia and dissolved oxygen, which is very low in wet season. That's because of a lot of activity, and rain or runoff bring a lot of contaminants from the terrestrial area, especially many pollutants from waste collection system or any other activity. So all of organics bring to the water and create the limit oxygen condition, which reduce the manganese from the ore into the water. So we found high manganese and also iron in the wet season. So we observe sand with different years. So the new sand image is on the left-hand side, and you can see that 1 year sand can have some coverage of the black color that stand for the manganese oxide. And in order to get fully occupation of the surface by the manganese oxide, you need 7 years. So it means that if you need to get good removal of manganese, you have to optimize the sand filter to be more than 7 years in order to get that. So what we do is that normally in the water treatment plant, they have more than 10 rapid sand filters. And what they do is that they mix between the new age sand that have a high rapid rate of the flow together with the old sand that have capability of remove of the manganese. And for the slow sand filter in Thailand, with really, really small scale, the picture is on the right hand side at the bottom that you can see this in the community scale. So they cannot remove most of the pollutants, and of course manganese is still present in the treated water. So the color of the sand is really black, covered with the manganese oxide, and we collect the sand that active on the surface after during the backwash process. So we get the sample and take it back to our lab and going for the experiment. And just simple column test that involved manganese removal through the physical attachment to the sand together with biological process. This the sand is already 8 years that used in the process. So all the setup is the same in rapid sand filter. And what we see is that by changing of manganese 2+ to manganese 4+ through the biological process, the size of the obtained manganese oxide is too small in nanosite range. So it's too small to be removed by the physical removal by the sand filtration. So we have to depend on the biological process. According to the breakthrough curve that fit on the left side, you can see that about 20% can be removed by the filters. So we try to separate what type of bacteria and microbial that work on removal of manganese by inoculate in the medium that rich in both manganese and iron for 1 week. The indicator of the turbid in the glassware indicated the growth of the bacteria that capable of utilize manganese and iron at the room temperature. Just to note you that room temperature in Thailand is about 28 and more, so it's greater than in Japan. And we try to separate by and then do the DNA extraction to get the bacteria and fungi community. So it should be noted that we first assume that bacteria played a big role, but actually several papers that published recently, fungi also can do that. So we separate about 7 isolation that comprise of bacteria in several species. Most are Bacillus, Enterobacter, and others. So it's quite interesting that if we employ the LBB reagents for the separation, that can allow the bacteria to grow either on liquid medium or solid medium. But what we found is that just only some species that can be grown on the liquid medium, but all the species or all isolation cannot grow on the solid medium. And this is just only few fraction of bacteria, because most of bacteria that capable of remove manganese cannot be countable with our exist method. So the color is an indicator of removal of manganese. So if no color change, it's no removal. So you can see that some tube have an indicator of color change compared to control. So the manganese removal is occur in the system. And we calculate the manganese removal by measure the initial manganese concentration and the final manganese concentration after that. And we found that there's a distribution of the removal capacities of the manganese by bacillus. The fraction is 4 that present on the table, but it contributes just only 20% of the total removals. So what you can see is that some of them actually are not just target for manganese removal, but some of them can even remove iron. So the removal of iron and manganese occur together with specific type of the bacteria. So we try to make it more insight into the phylum level and into genus level, compare between dry season, which is correct without rain, and a wet season in October. So you can see some difference in contribution of proteobacteria and for mycutes that make something that we make to go inside into the genus level. And of course, in the heat map that you can see different between B, which stands for dry, C stands for wet season. You can see that some part of bacteria cannot be countable. So this is still some gap of our current method that we have to go for in the next one. And we do triplicate sample. And most of the dominant species is the Dicholomonus and some that present in the Nivea bacteriums. So again, when we want to gain insight into what kind of contribution, so we come into conclusion that the bacteria that can oxidize iron actually can also do the manganese oxidize together. And then go for another coexisting contaminant in the water apart from the manganese. But please let me remind that manganese oxidizing bacteria needs to use organic carbon source for their utilization. So it's meaningful to see inside what type of organics that present in the water. And we use several techniques. That is the very simple one, the three-dimensional excitation emission matrix, that we can identify roughly the group of bacteria between the organics that present in the inlet of the rapid sand filter and in the backwash water. Why we collect from the backwash water? When the sand is backwash, all species, all oxide and organics that coverage on the sand will be refreshed and detached from the sand. So if we want to see what is already coated on the sand, it's better to see in the backwash water. And in the backwash water signal, we can see the presence of the microbial byproduct in backwater. And this is in the water treatment. So it means that even we put chlorine and we try to put some disinfectant to suppress the formation of biofilm. But actually biofilm is there, especially in the sand filter. So we do some characterization using ultra-high resolution mass spectrometry in order to separate the group of bacteria into two groups. So it's clearly distinct by the principal common analysis that the organics that present in the inlet of the sand filter is actually totally different from the one that present in the backwash water. So it's indicator that this organic is produced by the biological process when they oxidize the manganese and iron. And there's some indicator for the one that like to see the mass spectra. So different in the positive mode that we, and in the negative mode for the type of organics that present here. And now we try to see what type of organics that present dominantly in the dry and wet season. The idea is that if we want to reduce or accelerate the growth of the bacteria that capable of oxidize manganese, we don't need to wait for 7 or 8 years to develop the black sand, but we can make some inocula that enrich with organic matter together with the bacteria that in the group, in the consortium that can help to reduce the manganese. So this is in the future. Probably we not need to depend on the natural process until several or 8 years to develop that, but we can engineering the system that we can promote the growth of the particular bacteria by enrich the organics that can help them to grow faster than what we allowed the environment to do that. So this is maybe just my remark, and would like to welcome any question from the floor. Thank you.
Thank you, Associate Professor Dr. Jen Yuk. Is there any question from the audience? Yes, please.
Thank you very much for your very practical study. And my question is, has your result, how should I say, very optimized operation process is already applied to Thailand water works system?
Yeah, it's a very nice question. Thank you. Actually, there are only few plants in Thailand that remain or keep the black sand that enriched with manganese coated biofilm bacteria. So what they do is that they refresh the new one and they drop in the capacity to remove manganese. So what we do is now we confirm with the plant that still use this method to other that already replace the new sand. But what I want to give the message is that we don't need to wait for several years, but we can incorporate the bacteria that capable of remove manganese into the beads or encapsulate in some gels together with the nutrient that have the organics that they can utilize very fast and put it in the new sand system so that the small scale treatment plant even in Thailand or Japan can use this method so then they can achieve the high manganese removal since they start the operation. That is the idea and I want to disseminate this kind of idea to other plants in the remote area of Thailand as well.
Thank you very much.
ครับ
I think that is very good idea. Thank you.
Thank you ครับ
Thank you, Dr. Jen Yuk. I think we are going to have to move to the next speaker, which is Associate Professor Dr. Sawek Chai Tang Aram Wong from the Department of Civil Engineering, Faculty of Engineering. His talk is on development of sustainable concrete with recycling granite particle wastes. All yours.
Okay, thank you, Mr. Chairman, and good morning, everyone, especially the delegate from the host foundation, which is the Asahi Glass Foundation, who support the fundings through all the research that present today in this morning. And what I'd like to share with you today is about what the outcome of as the outcome of the funding that has been provided as a seeding fund to the project that we believe will help the constructions, especially the construction materials in Thailand, to look a bit more green. What we do, we focus on the concrete, and we try to use the recycling of the granite particles to be as a mixed ingredients in the concrete. Okay, I use this. The content of my talk today is very straightforward. First, I'd like to share with you the motivation behind why we propose the research in this topic here, and the objective that we have been proposed in the beginnings, and we come with the methodologies and the outcomes as what have been achieved in the last 2 years, and come with the conclusion and the future work. The motivations of our research that we propose here, we start to looking at on the top left, which is look really civilizations. We're talking about the building, the high-rise building structure, infrastructure that we use a lot, and we try to build the buildings and especially the high-rise building. And in order to have this to be achieved, we have to pay some price because our materials that we use in the constructions, we use what is called as a concrete. As you all know, concrete is one of the most toxic materials to the environment because it consumes a lot of the carbon footprint, and of course it consumes a lot of the natural resources. And one of these is we focus on the aggregate. Part of the ingredient inside the concrete, we have to take the aggregate as a main component. The aggregates, we have two types of the aggregate. One, we call them as a coarse aggregate. The other, we call them as a fine aggregate. In order to produce the coarse aggregate, we have to do something we call as a rock mining. And I show you here in the pictures, in the bottom middle, this is one of the sites that we have in some of the province in Thailand to produce the coarse aggregate. And on the top, which is very top right-hand side, this is the residuals, or we call them as a waste, as a byproduct of producing the coarse aggregate. And normally what has happened, this huge amount, this is just come only one mining site. It's accumulate each year more than 150,000 tons a year, and it has been put in the landfills that makes people who living close to these areas quite suffering with the air pollution because the particles that we have in the chunk of this look like the mountains is quite small, and it can blow to the air, and when people breathe this type of the particle, it doesn't look good to their health. So that's why this is come with the motivations why we come and revisit and to looking at in the mining, the rock mining, rather than we leave some of the residues on site, we try to bring this back and to put them back to the materials that we use in the construction. So we call them as a concrete. So, and if we're looking at it a bit closer, this is how it looks like. So it's not very fine. The gradation of this is some particle looks a bit quite big that you can see by eyes. Some particle look fine, it look like the powders. So the distribution of these materials is somehow quite tricky because if we use it in the concrete, we have to make sure the size of this, because it's in the intermediate level, it's not big, it's not too small. So we have to looking at how can we deal with this to make sure it doesn't jeopardize the good property of the concrete, especially in terms of safety. And we're looking at again the world consumption from the statistic, the consumption of the aggregate around the world. We're talking about 40 billion tons a year. And we're looking at in Thailand for the fine aggregate, we normally use a natural sand. Right, the natural sand is come from the river and is of course when it's damaged and it's depleting the river bed in the country. And we seem to thought that we almost run out of the sand in the future if we keep using the concrete and we're using the sand as a fine aggregate. So that's why in the project that we like to share with you today, we want to use this chunk of the particle to replace sand as a fine aggregate in the concrete. The way how we do is that we put in 3 equations as an objective of our projects here. We want to replace the natural sand with the granite particles, and this will be presenting as one of the mixtures in the concrete. And we target on 2 types of the strength. One is a low strength concrete. We're looking at the compressive strength, which is sits somehow not exceeding 250 kilogram per cubic centimeters, and we're looking at the higher strength, which is looking at about 50 KSC or the kilograms per cubic centimeters. The reason why we target on these 2 range, because in the low strength, we believe this will benefit most of the people in a lot of regions, because this is used for the low-rise up to the medium-rise building. And when we target a bit on the high strength, because we make the hope that it can be used for the medium rise up to the intermediate between medium rise and the high rise building. So that's why we target on these 2 strengths. And the thing that we have to discuss is about the functionality of the concrete. We talk in terms of the workabilities, how well it can flow when it has been poured on site. And we look at the mechanical property. This is provide the strength, is provide the safety of the material that has been used in the constructions. The first thing of all, we have to understand the gradation. As I mentioned at the beginning, the size of the particle is look a bit tricky, because when we put into the gradations, we call them as a sieve analysis. The sieve analysis means we want to test the size, whether how fine it is it too big or it's too fine. And we're looking at the standard, which is giving as a limit is a dashed line. If you're looking at here for the ASTM standard, the dashed line that's put as the upper bounds and the lower bounds here is tell the limitation of the fine aggregate that can be used as a construction material in the concrete. And what we find in the red colors, when we test a sieve analysis, the gradation of the granite particle, it doesn't fit very well with the bounds that has been told by the ASTM standard. So that's why we come and looking at, so rather than we can use it 100%, we try to use them as a fractions of the replacement. Rather than we replace the sand by 100%, we might try to deal with them to have some proportion between the percentage of replacement, and we have to use some of the sand. So that's why we come with the idea that we use it 20%, 30%, and up to 50%, because the 50% tell the gradation that it sit almost hitting the lower bounds that has been allowed in the standard that we told here. And after that, we're looking at the ingredients that we have to use in the mixtures. Of course, one is a cement. The other is a coarse aggregate, which is look like the rock, the granite rock. And the last one is the sand. And as we mentioned, that we replace the sand with some of the particles, which is the granite particles in the sand, starting from 20%, 30%, up to 50%. And we use the water to mix them together. And what we do, we have to determine first the percentage of the water that we can use. How we deal with this is we have to test what is called as a slump cone. The slump test that we do, the way how we test is that we pour the concrete that we mix into the slump cone, and we're looking at, after we remove the cone, how much of the deformations of the fresh concrete have been deformed. If it deforms a lot, what is happened is look like the concrete is look more like the water. So it does, it's flow really good. It can go through all the elements in the formwork very well, but the problem, it doesn't provide good strength. So that's why the level of the slump that we're looking at around 10 centimeters of the deformations. Then we start to determine what is the optimum percentage of the water per cement ratios, right, that can be used to produce. First is for the low strength. Second is for the high strength concrete, as what we target in the beginnings. And for the low strength, we do like the trial and error process here. It's quite time consuming, and it's coming that for the low strength, the optimum water cement ratio, we're looking at about 0.6. And for the high strength, we're looking at about 0.45. And after that, we determine this, we come with the ingredient of how much we have to use for the coarse aggregate, how much we have to use for the fine aggregate, and then we start to replace sand, which is the fine aggregate, with the ratio of 20% up to 50%, as what we discussed it. And then we need to test for the strength. The strength that we look at is first is a compressive strength, how well it can be resisting the force under the compressions. We're looking at the tensile strength, how well it can resisting the tensiles, and the last one is the fractural strength. So these three behavior we have been used a lot in the designs of the building. And we're looking at the strength at 28 days to make sure that after the concrete has been fully set, the strength can be gained at the same level as what the standard concrete has been used. And this is the test results to present here on the table on the left top hand side, which is presenting the compressive strength. It shows very comparable between L, which is the low. 0 is a percentage replacement. So 0 is mean we use 100% of the sand. 20 is mean we replace the sand by 20% of the granite particle up to 50, which is 50% of the replacement. H is standing for the high strength. So if we're looking at in overall for both the compression, tension, which is around 10% of the strength provided by the concrete in compressions, and the fractional strength. So these three presenting the strength of the materials is look quite comparable to the standard concrete that we use in the market. And when looking at the functionality of this, we're looking at how well it can absorb the water. We didn't want concrete to absorb the water very much, but when we're looking at in the graph, in the bar graph here, it look very comparable as well. So that's why this make our to have a confidence that it can be used as a replacement materials, as what we said in the beginning. After that, we want to have some more understanding. We go to the microstructures, and what we found is that the interfacial transition zone, or ITZ, of when we had the granite replacement, you're looking at the bottom diagram on the right-hand side, you see the little bit of the void, which is showing that when we're having the replacement of the particle as to the sand, we have some of the micro void in the concrete. So that's why it might have to take into the consideration in terms of the long-term effects and in terms of the corrosion that we represent them as a future work here. And in conclusion, we from the talk that I taught in the beginning here, we're quite confident that we can try to recycle rather than we dump them in the landfill to use them as a construction material for the granite particles. And we can replace the natural sand by 50%, and we can use them for both the high and the low strength that can be used in the construction industry. And this is providing more environmental friendly method to produce the materials. And the extension of this research funding, we have already looking at the post-fire response. So how well it can receiving the fire. And we're looking at what happens if we mix them with other type of the waste, let's say the fly ash, we call them as a geopolymer concrete, and to mix them with some of the fiber to provide a higher strength. So this might be in the future area that we're looking at from this seeding research here. And I would like to thank everyone for listening and for supporting the schemes here. Thank you very much.
Thank you, Professor Sawek Chai. Is there any question, please?
I have one question. Thank you very much. I think your result reveals weight is light due to porosity and high compressive strength and very good. My concern is, did you check the component of granite and natural sand? Because I guess there is a variety of deviation of component in natural resources, and it may impact on the properties of final compounds. How do you consider that?
The thing that we worry is that if you look at these diagrams here, it's presenting the physical properties between sand and the granite. You're looking at the red color. This is if we had the pure granite particle, it sits below the bound that has been acceptable by the standard, right? So what is happening if we replace them as 100%? It seems to jeopardize the strength, and that doesn't look good to be used to serve the people. But that's why we have to come with some type that we have to use some certain percentage of the sand, and we make sure that when we replace them, it just sit for the 50% that we propose as a maximum. It just hit the lower bounds, which is at the edge between can use and cannot be used.
I see. Okay.
Yes.
And one more very small question. Did you evaluate chemical durability or corrosion or erosion or other properties of final compounds?
We haven't looking at that, but this will sit in our future work. The reason for this, and what we believe is might have some problem, because when we look at the microstructures, you're seeing that when we replace the granite particle to the sand, it has some of the micro void. So we're afraid that when we put them in some of the hazardous areas, let's say that's very prone to the corrosions, it might have some effect to the concrete. But this sit in our future work.
One of my concerns is the boundary components with the matrix, cement, and the additives.
Yes.
I expect you.
Yeah. Now what
Maybe
we
porous characteristics might
have some
affect the durability for the concrete.
What we think so, and the thing that we have to do, we have to looking at how much is have an effect on this, whether it's very severe or it can be acceptable at some certain range. Thank you very much for your question.
Okay. Thank you. Thank you very much. I believe that this is the end of the session, and I would like to thank all the speakers and every one of you in the audience who gave the feedback to the speakers that are very useful ones. And as a chairperson today, I would like to close the session today, and please give a round of applause to all of the speakers and the audience too, please.